Welcome to the Walton Pie. Today we are going to be doing a challenge question. So our question today is, for any integer n, is it possible for both n plus 3 and n squared plus 3 to both be perfect cubes? So to start off, let's talk about different things that cubes have in common. So we can write a plus b cubed as a cubed plus 3a squared b plus 3ab squared plus b cubed. We also have Fermat's last theorem, which tells us that there are no integers x, y, and z, where x cubed plus y cubed equals z cubed. And from a previous video I have done on this channel, we know that we can write n cubed as the sum from k equals 1 to n of 3k times k minus 1 plus 1. Think about these and see if any of these give us a way to either try and prove that there is an integer n where n plus 3 and n squared plus 3 are both perfect cubes, or show it's impossible for that to work for any integer n. Take a moment, pause the video, and try and figure out this problem on your own. It's not very much fun to watch me solve this, but it's a lot more fun to be able to try it and see that you can actually do this on your own. I hope by now you've been able to figure this out, and that you're not just watching this video because you want to see the solution. If you're doing that, I'm serious. Pause the video and try and figure it out on your own. It'll be a lot more rewarding that way. But if you're completely stumped and don't know where to go, let's talk about this problem together. So let's start by assuming that we can write both n plus 3 and n squared plus 3 as perfect cubes. Well, that means that there are some integers a and b where a cubed equals n plus 3 and b cubed equals n squared plus 3. So let's try and figure out what values of n are going to work. So the first thing we might try is to see what happens if we add a cubed and b cubed. Well, if we do, then we get n squared plus n plus 6, which is cool, but it doesn't help us very clearly. Like, at least for me, looking at that doesn't tell me, oh, I know for sure that it is impossible for n to exist, or like, oh, that tells me that n has to be 3. Like, that's not something that I am able to see from that. So I would stop at this point and leave that alone, and if I continue to be stumped, try and see if I can use that somewhere else. Another thing I would try is to see what happens if I multiply the two together. So I have a cubed times b cubed. Well, that gives me n plus 3 times n squared plus 3, which is n cubed plus 3n squared plus 3n plus 9. And that looks pretty close to another cubic expression, but we'll talk about that in a second. Going back to the thing that I tried right before, where I added the a cubed and b cubed, the reason I did that was I was hoping that we would get something that would possibly look something like Fermat's last theorem, where we would get an x cubed plus y cubed equals something cubed, and then I would be able to immediately say, oh, Fermat's last theorem says that that is impossible. So if I was hoping that adding the two would get me something that would break Fermat's last theorem, which would tell me that it would be impossible. But unfortunately I didn't get that. Now, maybe doing some modifications would get me to something like that. So that would be something that I would look at to see if that would give me something that would help. So that's why I tried adding them in the first place. When I multiplied them together, that was just to see, is this going to be something similar? Because I am still hoping that it's going to break, because I think that it's impossible. Now, why do I think it's impossible? That was just my hunch at the first time I saw this. I saw this and my hunch was, I think it's impossible. So my goal is to try and assume it's possible and find a contradiction. Or maybe if I'm lucky and I was just wrong beforehand, I'll assume it's possible and solve for what values would work. But by multiplying the a cubed and the b cubed, I am hoping that I will get a similar thing also in the Fermat's last theorem, where I am assuming that z is a times b. So a cubed b cubed is just going to be my z cubed. I'm hoping that I will get the sum of two cubes out of n cubed plus 3n squared plus 3n plus 9? Well, we know from our a plus b cubed expression that we can write n plus 1 as n cubed plus 3n squared plus 3n plus 1, which helps us out quite a bit, because then we can write n cubed plus 3n squared plus 3n plus 9 as an n plus 1 cubed plus 8. And 8 is 2 cubed. So we've now gotten a times b all cubed is equal to n plus 1 cubed plus 2 cubed. We've gotten Fermat's last theorem's contradictory statement. We know it is impossible for integers to work like that, and we know n is an integer, we know 2 is an integer, we know n plus 1 is an integer, and we've assumed that a times b is also an integer, which tells us that something has to have broken. We can't change 2 to be an integer, we can't change 1 to be an integer. Our premise tells us that n has to be an integer, which tells us that a, b can't be integers. That tells us it's actually impossible. Now, this sort of process is the sort of thing that a lot of mathematicians have to do when doing a proof. You look at a statement, you make a guess, and then you just try and prove it. Now, you might go and have a few detours that don't go anywhere. Kind of like back here when we were looking at what happens if we add a cubed and b cubed. It was a good approach. It was trying to use Fermat's last theorem, something that we knew involved cubes, to try and get a contradiction. We just weren't successful with that. That doesn't mean that that's a bad way to think. It just means that that path didn't lead us to a contradiction as far as we had decided to travel down that path. That's not to say that there isn't a way to travel down that path to get a contradiction. It just says that we decided not to continue down that path, and that's perfectly fine. A lot of mathematics is trying different paths, seeing if they work, and in your textbooks, you only see the paths that worked. They're not going to put in a proof where they had all of their detours beforehand. They're going to do the succinct proof because they don't want to print a textbook that's the size of Walmart with all of the detours that they did or all the detours that anyone has ever done. They want to have clear examples of proofs that do work so that we can be able to see the process. So that tells us that it is impossible for there to be an integer n where n plus 3 and n squared plus 3 are both perfect cubes. I hope that was helpful and that you enjoyed this little video. Please stay tuned and subscribe so you don't miss the next time I put out one of these challenge videos. Have a great day and good luck with all of your math.